Hi everyone, welcome to part 2 of this video on differential equations in physics, where we're looking at the RC circuit. In our last part, in part 1, we had the switch closed at position A, and we sort of saw how the capacitor influences the behavior of this circuit when it's at position A. We saw that the charge on the capacitor increased, meaning that we were effectively charging the capacitor, pretty much. However, this time, we're going to try to see how to discharge this capacitor. How will changing the switch position affect the behavior of this circuit? So that's exactly what we're going to do here. So part 2. After maximum charge is reached, the switch moves to B at a new time t equals 0. So essentially, disregard this time t equals 0. We're restarting the timer here. And we're restarting this timer when the switch is now at position B. So as you can see here, this battery right here is pretty much just gone from the circuit. It's irrelevant now. The only thing that really matters is this loop right here. Basically, since this capacitor has maximum charge, it can sort of act like a battery for a little bit. And then over time, because of the resistor, it's going to lose some of that charge, and then it just goes back down to 0 over an infinite time span. So let's go ahead and take a look at that. So the voltage is going to be 0, as per usual. And so here's what's going to happen, right? So the change in voltage is equal to 0 because Kirchhoff's loop rule, not junction rule. That's for a different story. But here's what's going to happen. So this time, the initial voltage is just going to be the voltage of the capacitor minus the voltage of the resistor. Because the capacitor has charge now. So you're going to be gaining voltage as you move through this circuit. I also have the direction wrong. It'll go that way. So, therefore, we're going to have a Q over C, just like this, minus IR, because that is the charge across the resistor, or not the charge, the voltage drop across the resistor, is equal to 0. So, now what's going to happen is the charge per capacitance is going to be minus dq dt times R is equal to 0. But why did I draw parentheses around here? Well, here's the thing, right? The current is decreasing. So that means to keep things positive when we analyze the function, what's going to happen is we actually have to make this current negative. Now, why is that? Well, if we make the current negative, then what's going to happen is if we actually do the differential equation, we will not see an anomalic case of this charge and current increasing. That's not possible, especially with the resistor in play. So yeah, we have to make the current negative, and this works out because the current is decreasing, the charge is decreasing, and therefore the current is inherently negative. So to accommodate for that, we're gonna make this negative so that we can focus things in positive signs, just so everything works out. And as a result, the negative and the negative, they cancel out. So here's how it's gonna work. So we have Q over C plus R times dq over dt, and we have that plus just because we cancel the minus signs. Remember, current's negative, so we're going to remember current's negative because charge is decreasing. So we just accommodated for that, getting rid of the negatives. So now we have a simpler differential equation to work with. All that equals 0, okay? And we're going to do the same thing we did last time. We're going to separate the variables, except this time it's actually a lot easier. So R times dq over dt is equal to negative q over c. Same process as before. We're just going to multiply by negative rc, right? Or sorry, not negative rc, negative c, just to get rid of everything and keep q on its own. So we're going to have negative RC times dq over dt. This is going to be equal to just q. Now we're going to just move everything around. We're going to keep the dq here. We're going to move q such that it's on dq side, and we're going to move everything else out. So we're going to say that this is 1 over q times dq. We just divide both sides by q. This is going to be equal to, moving everything to the other side, this is going to be negative 1 over rc times dt. Same process as before. Now all we have to do is just integrate. So what's going to happen here? Well, the time is going to go from 0 to t because that's the initial condition for time. But the charge is a little bit different in terms of limits of integration. Remember, the charge is starting off with maximum charge. And we're going to say that we said that the maximum charge, or the charge it reaches after a very long time, that's equal to the capacitance times the EMF of the battery. Now it's weird though, because we're including the EMF of the battery even though it's kind of gone from the circuit. But remember, we were charging this circuit to the capacitance times EMF, and then we switched it. That's why the EMF is still kind of relevant. So this is going to go from C epsilon to just some variable quantity Q. And now I'm going to go ahead and shortcut this, because this is just going to be ln Q evaluated from C epsilon to some variable quantity Q. This is equal to negative T over RC. And then we apply the fundamental theorem of calculus, right? So this is going to be equal to ln Q over C epsilon. And you can see why we divide this in our last part. So, and you can see how this is equivalent to this as well. So ln Q over CE is equal to negative T over RC. And I should really be saying this is C times epsilon. My bad. And then we're just going to do the algebra here. Take e to the power of both sides. So then Q over C epsilon is equal to e to the negative T over RC. And as a result, the charge as a function of time for discharging is going to be equal to C epsilon e to the negative T over RC. And now we just do the same thing we did for calculating I that we did in part 1. So I, as a function of time, that's going to be equal to the derivative with respect to time of C epsilon e to the negative T over RC. And we do the same thing where we pretty much just go ahead and we move everything to the other side. So what we're going to do is we're going to say that this is equal to, this is going to be equal to negative epsilon over R e to the negative T over RC. But remember, we said initially current is inherently negative. This negative sign is redundant. So we're going to say that I, as a function of time, is actually epsilon over R e to the negative T over RC. And this focuses on the magnitude of the current, pretty much. So yeah, this right here, these are our expressions for the charge as a function of time and the current as a function of time. So with that in mind, let's go ahead and find when the current will be 0.05 amperes. So I don't have a calculator on me now, but what I'm going to do, I'm just going to leave it in terms of just magnitude. I'm not going to do any sort of numerical simplification. I'm just going to leave it as it is when I do the algebraic work. You can go ahead and find the numerical value on your own. I don't have a calculator, so what I'm going to do is we're just going to see when the current is 0.05 amperes. So we're solving for time given I. So let's go ahead and use this expression right here. So 0.05 is equal to epsilon over R e to the negative T over RC. So what this is going to be is, epsilon, that's 60 volts, R is 400 ohms, and capacitance C is 5 microfarads. So 0.05 is equal to 60 over 400 times e to the negative T times 400 times 5. And I'm going to say this is 5 times 10 to the negative 6 because micro means 10 to the negative 6. So I can go ahead and try to do some mental math here. So this is going to be equal to 0.15 e to the negative t over 400 times 5e negative 6. That's going to be 2000 e negative 6, which is 2e negative 3. So this is going to be equal to e to the negative 2000t. So therefore, what we're going to do here, we're just going to simplify this down to t. So what we're going to do is we're going to divide both sides by 0.5. So 0.15, sorry. 0.05 over 0.15 is equal to e to the negative 2000t. So, as a result, we can also simplify this to 1/3, because they're the same thing. This is equal to e to the negative 2000t. Now, to get rid of this e to the negative 2000t, or more specifically the e to the, we take the ln, or the natural log, on both sides. And by natural log properties, the ln and the e cancel, so we're left with negative 2000t is equal to ln of 1/3. So as a result, t is equal to negative 1 over 2000 ln 1/3. And this is also equal to, if you go ahead and use the logarithmic property, this is equal to ln 3 over 2000 seconds. And that's it. As you can see, as time passed, the current still decreased. Now, why was that? Well, the charge is slowly decaying through the resistor. And what I mean by that is the charges are leaving the capacitor. The capacitor acts like a battery now. So the charges leave it. They gain a little bit of voltage, but that voltage gain is negligible because the charges are leaving faster than they're coming back. So essentially what's happening is slowly the amount of charge just sort of decays, and that sort of charge decay turns into heat exerted by the resistor, and that's just by conservation of energy. And it's because the energy stored in the capacitor turns to heat energy because of the resistor. So pretty much what's happening is over time the charge flow slows down, meaning the current has to decrease along with the charge. So everything when discharging a capacitor is decreasing. So therefore, the time is equal to ln 3 over 2000 seconds. That makes sense. It makes sense that this 0.05 should be greater, or this should be at a further away time than the initial current. By the way, the initial current is 0.15. So, with that, that concludes this part as well on RC circuits. Hopefully you can sort of see how the world works in differential equations. This is obviously a very idealized example, but there are tons more examples out there. You can watch like 3 Blue 1 Brown's videos. He has a whole series on differential equations. It's pretty intriguing. I definitely recommend that. But yeah, that concludes this part and effectively, well, this series on differential equations in physics. I hope you enjoyed, and I hope to see you in future videos.